yesterday we discussed about the quantum vectors, how a quantum state can be represented in a vector, and it can be analogy. We see an analogy between the linear vector space to the quantum, and what are the properties holds. So yesterday when we are solving one problem, I just observed when we are taking the inner product. So if we are taking the inner product, let us say psi over phi, or when we are taking the phi over psi, so we should be very careful. These two are not equal. If we want to equal, we need to take the complex conjugative. So when you are taking the in the problem a over b or b over a, it will be 1. When I given I by 2 minus I by 2, you can substitute if it is this one. If this is I by 2, this can be minus I by 2 or vice versa. But we should be very careful. Pi over psi should be same. We have to write in this way. And when we are writing psi over phi, we need to be very careful. Otherwise, it will be the plus minus signs will be there. So that's the only thing. Is there any problem to solve the things assignment or that next problem I given? Hope it is clear. Is there any misunderstanding, any doubt in that yesterday's session? So I'm assuming everything is clear. Then we'll proceed to the quantum gate. So the quantum gates are similarly, if we are dealing with the normal computing classical, we also see some and or nor, all these the gates are there which are useful when we are writing a program. When we are solving that in a cascading or a particular sequence of operations executing, we are using kind of gates. In a sequence of gates and operation sequence, then we can say it as a computer programming. When we are writing the computer algorithm for quantum computer, so quantum computers also had some certain gates. So I here only given for which are useful for our next discussion in the algorithm. I'm not going to cover entire gates which are there in the quantum mechanics or quantum computing. So I just going to stress some of the gates which are useful for understanding the next quantum algorithm. So the quantum gates are the gates which will operate on a small qubits. So if it is a normal computing classical computing, that will deal with bits. So you are a computer engineer, you must know, you know these things. But when we are dealing with the quantum computing, it will deal with the qubits. So the quantum gates are logically operates on the qubits, small number of qubits, which are the sequence of operation. So these are irreversible, whereas the classical gates. But quantum gates are reversible. Quantum logic gates are represented by unitary matrix. So similarly, we can see some of the things. We'll just take a matrix and we can use, like suppose yesterday's quantum state is given, you know how to express that system of equation in a basis, and if it is a basic state is given to you, you can also know how to express in a matrix notation, coefficients multiplied by the basis. AX. So where A is the quotient matrix and X is the basis matrix. So the basis can be I, J, K, or phi, psi, chi, or something like that. So once you know the basis state, then if you know the gate matrix, then you can multiply or add or something based on the operation. So that is the purpose of this. The gates can be expressed in the unitary matrix. So we'll discuss about Hadamard gate, phase shift gate, controlled gates, uncontrolled gates also there in that controlled and controlled gate. And the operation, some of the operations also needed. So one is Oracle operation and Hadamard operation. Sometimes we call it as Hadamard operation also, which are essential. Mainly we'll use almost many of the quantum mechanics or quantum algorithms. They and Hadamard. So we'll see how the Hadamard gate and all the gates will be represented. It's like our simple mathematical formula. So A plus B whole square, how we are using the same thing. So these are the syntax we can say in the computer terminology. So if you know the syntax, we need to follow this when we are writing the sequence in a programming. So these are the gates. So if you take Hadamard gate, this gate operates on a single qubit, either state, suppose so state x is given or a bit 0 or 1. It will operate on a single qubit. Simultaneously also we can apply this Hadamard gate, but we'll see first how it will be operating. So it represented in the matrix. So this we can simply write it as 1, or if I take 1 by root 2 as common, 1 1 1 minus 1. The second column will be only the amplitude and first column will be always 1 1. So 1 over root 2. So this we can call it as the Hadamard operation. Not Hadamard H. We can simply represent this as H. If you see some of the things, if we encounter these things in the D'Alembert equation or some of the probabilistic model, so simply you can represent this in a H in the equation. So H is 1 by root 2, 1 1 1 minus 1. So that is the Hadamard operation. Then phase shift operation, sometimes we can call it as a rotation matrix also, or phase shift matrix. So we can represent it as R theta rotation matrix. When we are writing the algorithm for a circle line, if the line is shifted 30 degrees, 40 degrees, or the rotation. So when we are multiplying the rotation matrix, we are very much familiar with this. So here only the theta will be the phase angle. So how much phase is shifted, we can substitute that theta value in this equation. This matrix can be multiplied or pre or post multiplication with the given basis matrix. So we can, after completion of the operation, we can able to see that particular result are giving the transformation, whether it is a phase shift or the rotation. So transform matrix can be R basis or basis R, depending upon the situation. So suppose the basis matrix is A and R, where this R is this matrix. So and A matrix can be, suppose we can see, yesterday we saw some of the matrices, how we can represent, that is the basis matrix. Sorry, that is the coefficient matrix, not the basis. So we cannot multiply the basis x, y, or phi, psi. So we leave that basis matrix, only we'll take the coefficient matrix and operate that on the rotation matrix, whether it is a phase shift or the rotation. So then this we can call it as the transformed or the final result. Then we'll see the oracle function. Sorry, oh, there is one missing. Next one is the controlled gate and uncontrolled. So controlled one will be, suppose if we are writing the qubit, so if it is when we are it is performed by a controlled gate, simply it will remain as it is. Then is 1 0. When we are performing this controlled gate, we'll get it will take the second digit or the second qubit like this. So this can be written as 1, then the function is simple, the first qubit, then multiply by the x of 0 plus x of 1, that is 0 1 0 is there, so it will operate first one on the function, then take a addition, then this second one. So that is the controlled gate. Suppose if it is an uncontrolled gate, if it is 1 0, we'll get 0 1, or 0 0, simply we'll get same 0 0, or 1 0, we'll get 0 1, 1 1, we'll get same 1 1 1. So that is the uncontrolled gate. Then coming to the oracle operation, mostly this oracle operation can be operated to find out the success. Okay. So suppose if we given f of x is given, the domain so this belongs to in a range. Suppose the range is, let us take, the domain is V. So in the entire domain, when we are operating like our loop, when we are forming a loop in our normal our classical computing, we can apply some for loop or while, all these things. So now when we want to execute in this entire domain, we can operate this oracle function. So if it is function O, if we operate on the qubit x, so it will take minus 1 to the power of f of x. This is the given function f of x. In the entire domain, it will apply. So it will continue in the given range, in the given set of things, or what is the basis it will be dealing with. It will just take like a loop kind of thing. We'll see in the next maybe search algorithm, how the Oracle function is operating. So when we are searching for something in the entire domain, that time it will be very clear. So next we'll see the quantum parallelism. We also see the parallel computing in our classical computing method, or we can say some of the things are parallel computation. Usually we frequently hearing this parallel computing. Then what is difference that quantum computer is extra doing? Why we call it as quantum parallelism, which is not applicable for our classical computing. So suppose if a function is given f of x, so I will define f of x, then it is operating in a qubit 0 and 1. Then if we want to find out a f of 0, that's f of 1. So if we want to perform this operation in our classical computing thing, we'll take first the given function, we'll define that in the domain 0 and 1. Then we'll first evaluate this first step up to this f of 0. Then we'll take f of 1. In the next step, we'll take f of 0 plus f of 1. It will take a minimum of 3 steps. First f of 0, then f of 1, then it is addition of f of 0 and 1. These 3 steps. If it is a parallel computing, one of the output can be given as the input to the next computer. That we are usually calling it as a parallel computer. So first if it is taking f of 0, in other computer if it is calculating f of 1, then that output is given here, this so this is calculating the third step. But essentially it is also taking the same thing. Step 1, step 2, step 3. So that's what our classical computers does. But if it is a quantum computer, we can eliminate all these intermediate steps. We can simply, in a single step, we can evaluate this f of 0 plus f of 1. So that's the quantum parallelism. So it will take the parallel operation simultaneously. Why it is operating like this? Because of using the qubits quantum thing. So if we are doing all this in a parallel or in a single step, we can speed up this. That's what the quantum computers are known for, the very much faster when compared to the classical computing. So speed is increased and we can eliminate the intermediate processes. So we'll see that how the Dash algorithm will do this for us. So that is the parallel computing can be done using the Dash algorithm. So this is a circuit diagram for the Dash algorithm. It will take 4 steps. When same, I'm just taking the example of here f of 0, given the function f of x, and it is taking computing as f of 0 plus f of 1. So that is the basic example how the Dash algorithm can do in a single step using the quantum gates. So we saw some of the quantum gates, how we can write the circuit. So here it is given the qubits 0, 0. So when we take these 4 steps, then at the end of the thing, here we can get 0 plus 1. We'll see first. So this is the given. You can take anything, either 1 1 or 0 1 or 1 0, up to you. So we'll first here given the one qubit is given. First operation here Pauli check gate is operating on the qubit. So Pauli check gate is here. It will operate on the just a minute. So if it is we are operating on the first qubit is as it is. It is not taking any operation. It is directly going to the second operation. So I just mark here second. So since it is as it is, it keeps as this 0 as 0. But when we are applying this Pauli gate on the qubit, then at the end of this will get 0 transformed to 1. So at this stage means at this stage we are having 0 and 0 is replaced as 1 because of this operation 1. So we are having the end of the first process 0 1. If you have 1 and 1 you will get 1 0. If it is similarly you know that how to operate the Pauli test, it will just take that Pauli gate, it will just take the uh, if we apply on one qubit it will just give the reverse one. So then the end of the session, second operation, we are operating with the H and X. So two Hadamard operations we are doing. So we know the Hadamard operation. So applying on this qubit 0 and 1. So 0 plus 1 by root 2, 0 minus 1 by root 2. 1 is for this and 1 is for this. So this is the binary multiplication. So this is the binary addition. So after applying the Hadamard gate, we are applying the oracle function. So the oracle function, if we apply the oracle function here two qubits are there. This is the one and this is the two. But when we apply this minus 1, simply we have the circuit of this one minus 1 to the power of f of x. So we'll see intermediately how it is operating that Hadamard. After applying the Hadamard gate, first qubit and second qubit, how we apply the Hadamard gate. Then we are applying the oracle function. So once if it is oracle function is applying for this two qubits, so we'll have xy of f of x. So this is the oracle function operation. Then if we substitute f of x is equal to 1, we'll get this one. Simply minus 1 to the power of f of x and f and the bits 0 and 1. This is the function. These are the intermediate steps to understand how clearly it is operating. But as you can see, this oracle function is performing here. So minus 1 to the power of f of x, x and 0 and 1, 2 bits. But when we replace this x as 0 plus 1, 0 plus 1. So you can substitute minus 1 multiplying with this. So you leave this only this x, you can substitute this x as this one. So this multiply with this and this multiply with this. So that is the common thing. One second term, and this term is as this 0 1 0 1. We can previously we removed that 1 by root 2 when we are applying the Hadamard operation. So we'll get 1 over root 2. So finally here, after applying the Hadamard oracle operation, it is just applying in the entire domain. Hence, that is we are operating with 0 and 1. So it is taking f of 0 plus f of 1. Okay. So coming to the main circuit, at the end of this operation, we are having f of 0 plus f of 1. So binary addition. So this entire thing is happening in a single sequence or in a single process. So here we will get f of 0 plus f of 1. When we want to perform, even suppose there are two separate qubits, 0, let us say this is x and we want to f of x plus f of y. Similarly, we can operate all these gates. Then we may end up with binary addition of f of x plus f of y, when the x and y are the two qubits. If it is more, that will search in between that. That's what we are operating this oracle function. So just we when we are defining the oracle operation, it will take the entire domain in the search space or that region. So in that entire region, it will operate and it will calculate here. So that's what we are using the sign as binary addition and binary multiplication. So this binary addition and this binary uh, multiplication, it will just giving the superposition of a different constant or the superposition of states which are there in the entire space in the domain. So hello.
Hello, sir.
Yeah, can you hear me?
Yes, sir.
Okay. So here we can also define some of the functions if we are operating in a domain. Suppose the domain is 0 and 1 and our function is f of x. So our output is already defined. Suppose output is confirmed in this qubit, either 0 or 1. So we'll get our output only in between these two. Even input also something same, or we can give the substitute input value, but suppose we are expecting this is the one. When we are performing one operation, we are expecting that either x or y, yes or no, that kind of answer. So when f of x is equal, we know we know the output prediction. Suppose the output options are suppose fixed. Here we on either or one, either or no. If half of the time yes and half the times will no, exactly half the times will get yes, will get no. That means function is matching balanced function. So f x is, and whatever you will in the suppose possibilities for output. Suppose if we have 5 possibilities for the output, sometimes we'll get 2 and some other case will, that means unbalanced function. Understand what is the balance? Suppose we have yes or no of kind of thing. We have two options for the output. So half of the times we'll get one one possibility, then remaining half will get other possibility. In that kind of thing, we can say that function is balanced function. Remaining it will be unbalanced. Otherwise, it is unbalanced function. Suppose a function is there, whatever the input you give, you will only end up with one kind of one. Whatever the f of x, you will only get its value is 1. F of x is equal to 1 if you define like this. So either x can be anything, but your output is only one single, so that is constant. So this is a constant function. Or even if it is a f of x is equal to 0, whatever the value you substitute for x in the function, you will get only the single value. So that single value is defining that that function is a constant function. So this Dodge algorithm can also be find out to checking whether the balanced function, the output can be the balance or that. So we can check whether the here alpha is given, I think. Yeah. So you can see the balanced function or the constant. I said whatever the f of 0 is 1, f of 0 and 1, f of 1 and 1. So whatever the value you will give, you will end up with the output as 1. So that's why we call it as constant. Similarly for 0, even if you substitute whatever the value, you will end up with one single value, that is the constant value. Yeah? Otherwise, it is a balanced function. You will get balanced function. So if we operate whatever the qubit or the input you can take, only the output values, if you want to get in a superposition way. So you need to apply for this dash algorithm for the in parallel operation in the single circuit diagram. So this circuit remains same or changing, but you first apply the Pauling gate, then Hadamard, then Oracle, then you can able to get the superposition of this input value. So suppose if you have 1, 2, 3 states, so if you apply this, and after adamant and all these operations, we will end up f of 1 plus f of 0, f of 0 plus f of 1 plus f of 2 in a single operation. So that is the essentially this choice algorithm. This algorithm is known for the parallel computing. Is there any doubt? Is it clear?
Hello, hello.
Hello.
Hello, hello.
Yeah, hello. Am I audible?
Yes, sir. Audible, sir. Hello.
Yeah.
Sir, audible, sir.
Okay.
Please
Thank you.
carry on, sir.
Yeah. Okay. We'll So we'll discuss the next algorithm, Grover's algorithm. Actually, I'm not giving a practice session here. Just I want to discuss the three algorithms. This and you can practice and you can try to develop the code using the compound parallel thing. I'm just explaining the basic algorithm, how the performance is there, how it is taking the intermediate step. So the next algorithm is Grover's algorithm. So this Grover's algorithm is also known as the search algorithm. So this was developed in 1996. So what is the essentially this Grover's search algorithm is allows us and where we can apply this. So when we are trying to find even we can use the our classical theories. Suppose when we are taking a bookshelf, if we are arranging books in a ascending order, so we can simply go and take a small book wherever whenever you want to read that book, you can go and take it that book easily. But if you arrange the books in a random way, so some of the small book is hide behind that some of the books. So it is very difficult to take the book or identify the book. It is not it is not impossible to take the book, but it is very difficult. You can go and it will take some time. So that is what this. But book without searching the page. Okay. How this algorithms work in our classical computing? We'll first for search algorithm. Suppose if we are searching for something, we are searching for a telephone directory. We are searching a name. So first it will go and take on the alphabet A. It will check our alphabet. Suppose if we are checking for uh, some name is Bombay. So it will first go in the alphabet. It is since it is the input is given in a systematic way. The input is a range from alphabet A to alphabet Z. So in that domain, it is operating for searching for particular Bombay B. That is our essential object or our target. So our target is Bombay, but we have the domain from A to Z. So if it is our classical computer, if we write a code for that, simply it will go and take one particular letter or first whatever it is comes to pick up, then it will compare for our target. So we need to give that comparison. If that is there, then we'll kill the program there itself, means we'll stop the termination. Then it has to retrieve. So that has to print for us. That is our output. So in this way, we'll apply for a loop. So in the entire, it will just take and compare. If the comparison is matched, then we'll terminate the program. So in this way, we'll write that for classical thing. But when we are looking for B, Bombay, in the alphabet A to Z, how it is operating? It will just go whatever the letters are there in the A, alphabet A, first it will compare with our target as Bombay. So first it will pick up whatever there in the first letter A, then take that, compare with Bombay, our target, then it is not matching, then it will continue in the next loop, then it will go and take the second one, then it is come and compare with the target, still it is not matching. In this way, it goes on. So this way, our classical computers work for searching, or we'll write a code or develop a code for particularly finding that. But if you imagine A to Z, alphabet A to Z, there are a lot of search space is our search domain is more, then it will take a lot of time. And our speed every time it will be with the same speed, it will continue, it will take time. So in this way we cannot able to find a random way, we cannot go and check, it will if it is a random, we cannot able to write a complete program. Sometimes we may miss our target. If we are checking in a random, may chance of taking, it will take and it will completely take search in the entire domain, but it will take some time since we are doing in a systematic comparison. So what Grover's algorithm will do, it will not go and touch the periphery of that word, means it will not go and take the entire alphabet in the first letter A and come and compare with the our target. What it will do is it will just take in the entire domain. For that we have the oracle operation for looping. So we'll apply the oracle in the entire search domain, it will check. Then our target is there. So for that we'll go for that particular gate Adama. Then it will just take comparison whether it is matching with our target or not. Simply it will take the periphery, it will not go and take the entire bit, entire qubit or the entire value what is assigned in that particular register. So in that way, the Grover's algorithm will be very faster. It operates speed of a root n time faster than classical computer. But the procedure similar, only the except the speed, the remaining algorithm, how we are comparing, how they are searching, it will be very much similar. The analogy is same, but the process is different. We are just taking that the process, instead of going in a simple loop, which is familiar with us, what we can apply a loop in that our classical computer. Instead of that, it will just take in the oracle gate. So this operation will be much similar and in a faster way, a root of n time. faster this Grover's algorithm will work when compared to the classical algorithm. So essentially, these things are useful for finding the names in a telephone directory. So this can be there. The telephone directory is a structured way of arranging. That means in arranged data, it is easy to pick up. Sometimes, if it is our match, simply I said our object is Bombay. So it is starting with B. So we know that we can terminate the program. Instead of searching for A to Z, we can simply write another program in between the within the loop. We can check only in the B since it is arranged data. So it is arranged from A to Z. So we can check only the B letter, then compare there in the B with the target Bombay. So it will go and pick the value and compare the value. Then in that way, we can at least minimize the time process finding the process of this one, but it will only possible for the arranged data or a structured data. But if it is a randomized data, it's very difficult to execute this program. But Grover's algorithm will be equally applicable for the structured and unstructured data. It will be in the entire, it will be randomly checking that. We'll see the circuit diagram, then it will be clear how we can understand that. So this salesman finding the route. So for finding this is one of the application for this. So I just given here in between steps. I'll just go for the circuit diagram. I simplified the circuit diagram here. How the Grover's algorithm works. Suppose I just taken the example of same in the telephone directory. We are checking for the yeah, in the telephone directory we are checking for the particular name. So this one, these are the inputs. So what is we want to looking for, we'll give that as the input, and we have the search domain. This is our entire directory. So in this we are looking for this particular thing. So we need to extract our target from this workspace. So for that we need to check each and every corner of this space. We need to extract for our target. So for that we will first apply the Oracle function. So this one, then Hadamard gate, then this Polish gate at the phase shift. So if we it is just like our comparison, 0 matches 0, then it will stop here. If it is greater than, means it will be just reverse the sign and it will continue the loop. In this way it will compare. If it is compare, we can just print that is our value. So that is our Hadamard operation again. So the Grover's algorithm first will supply the qubit, n qubit. So it may be single or dual. So these are the input or target or our objective. Then once we apply the Oracle gate or Oracle function, then it will create a loop within the workspace. So we'll call that as the Oracle workspace. So since we are operating with that, so in the Oracle workspace, it will essentially loop. It will pick up that if we take the value and assigning that to the edge, that is the diamond operation. So in the workspace, suppose it is taking this value, then this value is assigning as a edge. Then it will compare the phase shift gate. So if it is H, it means our target is also same, then it will stop here. If not, then it will phase change. It will operate, then it will go and pick up another value. Then again it is assigned to the H, then it will do the same operation. Then if it is matching, then it will stop. Otherwise, it will go and change the value. Here, means it will change its sign and it will go and take another value. In that way, it will operate. But only thing is that we are eliminating, suppose our normal classical computers are doing 4 times, so square root of 4. So this classical computer will do 4 times this function, means it will pick up 4 times and it will be completing. Instead of that, this Grover's algorithm will do only square root of 4 times. So in this much is the speed of that thing. Since we are operating in this way, instead of go and check in a systematic manner, it will just take the value which is assigned to this adamant. You can see here. So the step of the Grover's algorithms are: first, apply the oracle function. So first you apply the set oracle such a way that it can recognize what we are looking for the search. Then Hadamard transform. Hadamard transform is which have applied so this will look for the qubit. Then that qubit will take from the search space. Then it will add here. And then compare here. If it is matching, then it will stop. Otherwise, the loop can be continued. Hello.
Hello, sir. Hello, sir. Hello. Hello, sir. Hello, sir. Your audio is not visible, sir. Hello. Hello, sir.
Hello, madam. Can you hear me?
Yes, sir.
Okay. I lost 4-5 minutes.
Yes, sir.
I'm trying to see.
Ah.
So So
After 3 minutes, you cannot listen, sir.
yeah, okay. Some internet error.
Please share your screen also, sir.
Okay, so
It is visible, sir.
yeah,
Carry on, sir. Please carry on, sir. Hello, sir. Hello, Kiran,
yeah,
sir.
yeah. Hello, madam.
Yes, sir. Some
Yeah,
network
there is.
problem, I think, sir.
Yeah, I cannot even. Okay. Will if, when is the break actually?
Yes, sir. Carry on, sir. In this hour.
It's at 11.
Yes, sir.
Okay, we'll try to stay until 11:15 or something. We'll try to finish the remaining thing, then we'll take complete thing. Is that okay?
Yes, sir. Okay, sir.
Okay. Yeah. Uh, so we saw just how we can parallel computing and just repeating last 4 minutes something. So I think Joyce algorithm is clear. So here we saw essentially how we can compute the uh, sequence in a how we can do the parallel computing in a given range or in a given domain. So if we are looking for the parallel sequence thing, we can just go with the sequence of gates. So we can essentially will get the superposition in a sequence. So that superposition it will either addition or subtraction. So binary addition can be possible. Similarly, we can do for the multiplication these things also. That essentially it will allow us for the parallel computing. So that is the dash algorithm. Then we also see how the Grover's algorithm allows us how fast it will compute for searching. So we can also call it a search engine kind of search algorithm. So essentially we are searching in a domain for a particular thing in a randomized arranged data. So we'll first we saw some sequence of operation. Mainly we'll first Hadamard operation is essential for just taking and picking the value assigning to that. To create the loop, we are following for the oracle operation. So with that oracle operation, we create kind of a loop in that entire workspace, oracle space. We are checking in a random way. Then we are assigning that with the help of Hadamard gate. Then that assigned value we are comparing with the phase that is controlled uncontrolled gate, both controlled and uncontrolled. If it is the phase shift, the control, it will be assigning and compare. So then it will terminate the program. If it is not, then it will go for uncontrolled gate. Then phase change will happen. Then the time they go and continue for the search. So that is the Grover's algorithm. Then The next algorithm is Shor's algorithm. So the Shor's algorithm is used for factorization. So we can also call Shor's algorithm or Shor's factorization. So the Shor's factorization is used for the factorizing the given number. Suppose if a given hello, yeah. Suppose if a number is given to us, when we are looking for the factorizing for that in a prime number. Suppose if you take 6 as the number, then we'll take its factor 2, 3, both are prime 1. So this 2 into 3 and 1 also be there for any number. So 1, 2, 3 are the prime factor for the 6, but 1 is not taken. So 2 and 3 are the factor. So when we are finding the factorizing for a given number, this Shor's factorization or Shor's algorithm will be helpful. So this is very recently developed using the quantum computer. We can write a program with our normal computing facilities and in a classical computer, but using the quantum computer, how fast it can be developed. IBM and Microsoft recently shown demonstrated for this factorizing for the number 15, 3, 5. So these are the two factors for that one. So within a short span of given time, so it will take and give the factor for that 15. So in 2015 or something, that developed this thing for the factorizing. So we cannot optimally use this algorithm for comparison or for using for particularly in our computing thing, but only it will be useful for generating the factorizer factors. So for that, Shor's algorithm can be helpful, but before writing the Shor's algorithm, we can also take the help of the classical computer. So in a given number, when we are looking for the factorizing for that particular number, so we'll take that number and we'll try to solve in a classical computer some of the program. Once we generated that essential thing, which is input for the quantum algorithm, then we'll take the help of the quantum algorithm to solve that particular thing. So here two steps are basically it consists of two steps. One is first part will be in the classical computer and the second part can be done in the quantum computer. So for classical computer, we'll take the factor or the number and reduce to the factoring problem, like order finding, which kind of factors we are looking for. We need to just redefine that as it is. Suppose the given number is suppose 6 or 15 or n. So the n number we cannot simply give it to the quantum algorithm and ask it to solve finding the factorization. Instead of that, we can just take that and in a classical computer, we'll just redefine, we'll make it is computable in the quantum computer using the quantum algorithm. We'll see how it is. First step is classical computer or the work using with the classical computer. We'll take this one. We are defining the order, reorientation and for the given number. Then this will be fed to the quantum computer for getting the factors with that particular number. So for the classical part, take the given number, pick any random number. Suppose we are looking for the number n, our given number. So our given number is n. So we are finding the factor for this.
Hello, sir. Hello. Kiran, sir. Hello, sir. Your voice is not visible, sir.
So when this assign, hello,
Hello, sir. Your voice is not visible.
okay,
Not audible.
okay. So okay, I'll start.
Start quantum computing part onwards, sir.
Okay, so
Take n value.
no, okay, sorry. So when a number n is given for us, so we are finding the factor for this number n. So for that, we just discussed, it is essentially doing the two parts. First part will be in the classical computer, then we'll make it as a factorizing order, then that will be solved using the quantum computer. Simply, you may say that why this number 6, 5, it is very easy. We can also write the simple code for that to find out the factor, and we can easily generate. But please imagine that when you are solving a research problem, you can see in that some of the functions will be there in that. So the function itself is another function. So we are generating the factors in terms of the function. So in that case, it will be helpful. Otherwise, for the simple numbers and all, I just take an example for the simple number so that you can understand how we can take 6 as 2 and 3 are there simple factors. But if you take a particular problem which is having a big with, special mathematical function, so in that special mathematical function, you will have there uh, for solving particular one particular thing itself very difficult using the special function, Bessel function, all these things. So if you imagine that Bessel function on the other thing, when we are writing the particularly wave equation, when we want to solve Schrodinger wave equation or a wave diffraction, so in that particular case, the problem will be very much complicated. And if it is only interaction with the two-dimensional, like only water and air, or air and any kind of material, like if the wave is propagating through the uh, alumina or steel, any metal, the wave is entering into the air. So it will be only having one fundamental longitudinal mode. There will be not any shear mode in the wave propagation in the simple air. But if the same wave is propagating in a solid, then it will be having lot of modes will be generated. Shear mode, and in that again there are lot of higher order modes will be generated. So each mode we want to generate the mode shape, how the characteristics of that particular material when assigned particularly when the wave is propagating in that. Or how the suppose if the wave encounter any artifact anomaly like a material density changes or a particular void is there or a crack is there. So when the wave go and hit the crack, then the wave will be wave diffraction will happen. Instead of wave diffraction, there will be wave encounter simultaneously diffraction, refraction, and some of the other things. So we can call this as the wave dispersion. So when we want to solve this particular equation, we need to use the special function, Bessel functions and all, take that. Then if we want to take the factorization in that particular domain, so that entire thing it will be again function of function. So suppose this will be having the two functions. The factors will be x and y, but this x is again a function of f of a or something. Then this may be y be also something like that. So in that case, this algorithm can be used. So that's what you can see here. So first, for making it simple, take the n is a number instead of a function. So if we want to generate the factor for that particular thing, we'll take a random number, then we'll compare that. So suppose if we are taking the factor for that name number, so n can be the factor for n and 1 can be the factor for x. So the number itself will be the factor and the 1 can be the factor for everything. So we are looking for the factor and that to prime factor. So that means the number can be less than or equal to that. Equal to that means that will be the same number will be there. So when we are taking a random number, we can first check that it will be less than that number. Then we can compute using the classical computer greatest common divisor, the GPD of that whether it can be divisible or not, that number. It may be done using this algorithm. If the greatest common divisor is not equal to 1, that this number, then there is a non-trivial factor for n. If it is 1, then it will be substituting the within the fine range within some period. So then we'll generate the function f of x. Can write this function as like this. So this a is our random value. Then we are writing the function in terms of x. Then this is the n is the our given value which we are looking for the factor. So then we'll take the smallest integer r. Then we'll compare f of x plus r is equal to x. So that means we are just adding small value to that. We are finding whether means we are checking for the factor whether this can be there, and then we can add delta x, delta x, delta x. So we can just we are starting with one particular random value. Then that is if that is the factor or not using the classical thing. We'll check. Then if it is not, we'll simply increase that number. Then we'll compare whether it is there or not, the factorization. So in that way we can compare. Then once if it is that we generate this one, we cannot solve this particular problem. Then this can be done feed to the quantum computer. That is the second part. So in the second part, we can find that same thing. Here we can give it to the quantum algorithm and it will apply the quantum Fourier. In the first, when we are discussing with the quantum gates and operations, so we saw some of the Hadamard and Oracle and conventional unconditional gates. So there is also possible for the quantum Fourier transform, which is can leave it. It will be much complicated. So I didn't touch quantum Fourier transform. How we can see this. Similarly for our classical, how we can express the terms in terms of cosines and sine, the series. So you can also see the quantum Fourier transform. I also given one reference. You can see that how, if you are interested, you can go through. So how we can apply the quantum Fourier transform. This essentially do that, like I said, that in the storage in the register, each value it is increasing, comparing whether these are the factor or not in the qubit. Then this Fourier transform will help in the finding the checking for the particular storage in the particular assigned register. So you can see that how the Fourier transform can be applied using this. Here it will be, I feel like, how can I explain this? So if it is a simple operation, this one, if we apply the Fourier transform, then it will make this is theta kind of thing. Then it will transform into this. Then the Fourier transform will just leave the part of that Fourier transform. If you didn't familiar with that, it will be very difficult. Okay, it is also in the introduction how we can perform that one. Okay. So once it apply the Fourier transform, essentially just it will give us the roots in the, like we said, in this manner, x increasing the r. So essentially it is f of x comparing when r will be the next multiplier, smaller value addition, then it is comparing whether it can be the factor or not. So then whenever we had this, this is the why we are using the functions in this. Simply when we took a number here, simple number, then we are making it as a function. But if it is a simple number, like I said, 6, 5 or 15 or a number, we may not have this much complication here. But like I said, some of the examples, this n is a function of certain, that x and y. So we are taking this function x separate and y separate or something, a factorization. So these are the two factors for this function. So in that way, function itself is a functional. So for particularly for that particular thing, in that case, when we are writing that, so this is essential, and the Fourier transform will be there to check in the storage values in that particular register. Okay, here is the quantum company second. Okay, there is anything that ordering system. I will give that updated thing to this organizer, then they will circulate that PPT. But you can see this one. So this is a very neatly explained in this book, quantum computation and quantum information. So if you see this, you can able to see how this quantum and how computation is happening, can be done, and simple examples also illustrated. You can practice how we can here search algorithm is with one or two examples. Then it will be very clear. Is there any doubt? Even in the previous section also, yesterday's session, linear vector space and the problem. The Dirac notation and dual space.
Sir,
Yeah, hello madam.
so the reference book, sir, once again, asking one of the participation.
Okay.
You about
Yeah, this I will send. You can circulate this entire PPT to you all. You will
okay,
get
sir.
if I'll add this also here. There is some distorted PPT even in somewhere that unconditional conditional gets also missed here. I'll update that and I'll send it to you again so you can circulate to the participant.
Okay, sir.
Thank you. Is there any clarification is needed? Even in the hope this is clear.
Is sir clear about all? Thank you, sir. Shall
Yeah,
we
thank
take
you.
break, sir?
Yeah.
Okay.
Yeah. Thank
Next section will start 11:30. Please join before 5 minutes. Thank you, sir. It's
Yeah.
clear explanation, sir.
Yeah. Thank
Thank you. Next session will 11:30. Please join 11:25. Thank you. Hello. Hello, Kiran sir. Hello. Hello, sir. Hello, Kiran sir. Hello, sir. Hello, sir. My voice is audible, sir. Hello, sir. Voice is visible, sir. Audible, sir. Your voice is not audible, sir. Sir, please unmute your mic, sir.
Okay.
Ah,
Is it okay now? Sorry.
okay, sir.
Okay.
Your screen also visible, sir.
Okay. Thank you.
Okay. Please carry on, sir.
Okay. Yeah. Hello. Welcome again. Uh, so actually, 12:40, 12:30, I need to have odd staff. 1 o'clock, I have another review. So I didn't ask organizer for the hands-on session. So it is very difficult to practice the algorithm without the specific codes or some of the other software installed in that. So hence I have here any 40-45 minutes of time now. So with this short time, we cannot practice much with an algorithm or anything. So what I got a couple of requests also. So yesterday's thing, just 1 or 2 example, stress on that. So I decided with the permission of organizer. So we'll just repeat that yesterday's, just highlight that yesterday's session. then we'll work out another problem. Then if possible, we can see this algorithm repetition with some insights with some overview. So hope this is okay and clear to all. Or else if you have any specific doubt, please feel free to ask. We'll discuss on particularly there on. Hello. Okay. So we'll see. In last lecture, yesterday, I just discussed first given the introduction of the linear vector space. This is just a recap from our school mathematics. So we know how to solve the vectors and all. From that, I try to define the quantum state. Then how we can see the dual nature of the particular quantum state and how it is related to the vector space and what are the analogies between the linear vector space and the quantum state of mechanics. So with that, we all seen this some of these vector. So we know some of the properties of the vector. So suppose if the vectors are given, if we add two vectors, then the new vector, the resultant vector, is also belongs to the same space with the fundamental or the master or the parent vector which are belongs to the vector space capital V. So and if we add two vectors, then multi-scalar or even we can individually and associative and commutative properties also holds good. When we are doing this commutative property for the quantum thing, addition is okay, but when we are doing the fundamental and dual state, that time we need to be a little bit careful. But in the linear vector space, the commutative property holds good. So we also discuss if a arbitrary vector is given, let us take that arbitrary vector be R. So if R can be expressed as a linear combination of given vectors. If we are able to write that, then the system is called as linearly independent vector, not dependent vector. So that means linearly independent vector. If we are able to express the arbitrary vector as the linear combination of vector, then it is the linearly dependent vector. If we are not able to express that, that means the quotients are 0, then we can say that the given vector is the vector system. The vectorial given systems are linearly independent. There is no relation between one and another. That's what the meaning. So linearly independent. Then it will not depend on other. So it is linearly independent system. The vectors are linearly independent vector system. So number of linearly independent vectors in the domain decides the space of that vector dimension. So suppose if a given vectors there are two independent vector spaces, then that means it is two-dimensional. Likewise, we have n number of n-dimensional vectors. So here I give an example of three-dimensional which we are familiar. So we can take that three vector space. So for the basis, when we want to express the vector, we decide just now we see the number of independent vectors decides the dimension. So now we know the n dimension, whether which dimension of that vector space. So when we want to express that vector in the domain, so we need to follow certain basis. So there are certain principles to express the vector using the basis set. So basis can be, it has to span the space, it has to be independent. It no need to be orthogonal system. It can be anything. Still we can express the basis. Suppose if we take here for R3 or famous three-dimensional space, x, y, z are the three coordinates. So these three are the basis. So then these three also orthogonal or orthonormal. Suppose if we write x, so if we have this system x, x plus y by root 2, x plus y plus z by root 2, I am having the denominator, making it as the unit vector. So I am just taking the magnitude so that it will become a unit vector. So if we have the first set of things, then we can use that x, y, z are the basis for the vector domain or the vector space, which here the properties are, these are three-dimensional vectors which spans the space. So using this basis we can represent any vector, and these are orthogonal or orthonormal. But in the second step we have the same vector basis. We can use this basis if we express this any vector using this basis system. Still we can use, but if it is x is this one, assume it as horizontal line. Sorry. So x plus y by root 2. If it is y is this way, so x plus y by root 2 may be somewhere here. So this x and x plus iy is not orthogonal. It is having some theta. So it is not perpendicular to each other. That means these are not orthogonal, but still we can use it for the basis to represent a vector. So this is the representation of the vector. So which can be the basis, which cannot be the basis. We can use this. And we also discussed about the dot product. So dot product considered as the inner product. Using that we can get the scalar value. So that essentially if we take the same vector, multiply with the same, since dot product of the same vector can be one scalar, and square root of that value gives us the length of the vector or norm of the vector, which can be denoted by square root of mod a, mod b and cos theta, or simply we can denote this one. So we know if a given vector is there, we can able to calculate its length or the norm of that one. Then if we want to define a state of a quantum mechanical system, actually if we are writing a particle in a continuous motion, so we are defining at time t, at time t1, the state of the quantum mechanical system is here. At time t2, then the system changes from this to this position. So when we want to express like a deterministic value, Here we are finding the value at this particular location at time t is equal to t. So we can express this function is a size. So we can write this as the ket. This is the Dirac notation. Ket psi. Actually, we need to write psi of t. The t can be t is equal to t1 or t is equal to t2. Just a minute.
Sir, Kiran sir, your voice is not audible, sir.
Can you see my screen?
Yes, sir.
Sorry, it automatically went on mute, so I'm speaking. So when we are taking this uh, quantum mechanical state, actually we need to be very much time dependent. So because it is varies, it is not a constant thing. It will be continuous motion. Or if you take a particle in box or wave motion or anything in a quantum way, so are exciting the one state. Suppose it is exciting one state to another state in the intermediate state. So anything can be possible, but we need to be with particularly for that particular state only. It is not a constant value. It is continuously ever changing with respect to time. So here given the three positions like phi, psi, chi, all these things maybe with different values or it can be at a different time interval. So that's the meaning actually. So next, if we have this, then we saw some of the properties. We can add them, and the resultant position can be within the same domain. So if you take the position at this time and position at this, and if you take combined position also within the same domain, so it cannot be the any stranger value. And we saw some of the scalar multiplication, how it can be there. And it can be holds good for the associative property. you can add that any way. So you can add first two and then the resultant one can be the remaining. Add can be add with the remaining, or you can add the last two, then you can go. Any order is not a matter. So that is associative property. And then null vector is same for even for the linear vector space also. If you take the vector and add something, then it is not changing its value, then that addition value is called null vector. So then we define the dual vector space. Suppose if we have a particular state, right, it is also had its dual nature. So this is called ket type. So its dual nature can be represented like this. So its dual nature can be called as prasa, its reverse sign. So this dual nature is possible for the particular uh, nature when we are writing this, defining all the uh, expressing that in a particle nature, try to uh, address some of the issues like diffraction or something, then we go for the wave mechanics. But some of the things we also follow the particle nature. Sometimes we take both the dual nature, both particle and wave nature can be exist, and depending upon our convenience, we'll follow the system. So here each state can have its dual nature. So the dual nature can be represented like this. So bra ket psi can be represented as its dual nature bra psi, or bra psi can be there ket psi. So then we can add some of the properties. So simply if it is a simple, suppose if we have a basis vector, then ket psi can be expressed. Actually, when we are writing the quantum mechanical state, usually we'll get like this. Actually, if it is the basis is ijk, for simplicity I'm taking. So xi, so I'm taking x1i, so x2j, and then I am not using mouse, only my cursor is at x3k. So these are actually ijk, all the basics. Just we decided how we can see the basis vector. So this state can be further write in this way. So this one will be as this one, and here I j k. So this is the basis set. So we, for calculation purpose, we neglect this basis set. We'll take only the magnitude or the coefficient value. So that is given here. So if it is, we know this one for a particular state, its dual nature can be its simple transpose if the member is a real one. So simply you can see here its dual nature can be expressed like this. But if the for representing the quantum computing or position of the quantum state, like here you see this is a complete state in a three-dimensional. If it is n-dimensional, one particular state psi of t is equal to t1 or t, it can be expressed like this if it continues for n-dimensional. So on. So. But yeah, so when we want to define this complete state, so this question may not be real. If we want to express the state completely, it can be associated with this complex number. Suppose if you take the vibration, so its real part can be represented its amplitude, then the imaginary part can be represented its viscoelastic nature. or the dash point are the damping property. So if it is that vibration, suppose if it is the wave propagation, so amplitude of the wave can be the real part can be represented and the imaginary part can be represented its wave dilution, how much energy is lasting when the wave is propagating. So in that way, completely it can be, suppose if you are writing this question, it can be x1 plus that I is not with this I, don't confuse, this is imaginary. I'm just representing with this one is cap, I cap, j cap, k cap. That will be the unit vector representation, you know. This is not a, so x plus I y1, where I is the imaginary number and y1 will be the imaginary value and x1 will be the real value. So most of the simplicity we will deal with the real number. But to represent the state completely, we can also have sometimes the imaginary value, a particular value can be the 0, so that one will remain only the real value. But it can be also possible there will be complex number associated with that. So if it is a complex number, when we are expressing its real nature, we need to take its complex conjugative. That is there expressed here clearly. You can see here. So if it is the complex number, we can see this one. So then we can find out their inner product like this. Suppose we are writing this, we have a size, this is sketch size. If we write a bra size near to that, we are calling this as a inner product. Suppose this can also possible. But we discuss only this one. This will be the scalar one. So this will be going for the, if you calculate similar that same this way and take real nature and this one, this will give as a vector one. So it can be possible, but we are not dealing with that. Just I shown here only that scalar multiplication or the inner product, because just we want to define the length of that particular one. Suppose in particularly when we are expressing the quantum state in a wave motion confirmed in a particle or the box, or hydrogen particle is jumping from one state to another state in between the state. When we want to calculate the energy emission, all these things, so we can take particular state and it, but what is the value at that particular thing. So that length or the norm of that particular value can be helpful for us. So on that particular reason, I shown here only this this sign, but this also be possible. So in this way, we can express their inner product. If it is a complex number, simply we need to take their mod. So then suppose if it exists like this, we can take x1 square plus y1 square. So that will give that their that mod value. That means that can give the real value of that one. So finally we'll end up with this one scalar with real number. Then we see this property also. So simply phi size cannot be equal to phi size. This can be its complex conjugative. Since we are dealing with here, you can see that clearly illustrated here. So if you take the complex conjugative of this one, a1 star a1, if you take the star on this one, or its complex conjugate when we are writing, you will get this one. A1 star star is A1 simply, then B1 star. So B1 star A1. Similarly, you will get this one. So in that way it will prove. So this a complex, suppose if we are taken a triangle, no need to be a right angle triangle. I just taking for easy. We mostly deal with Pythagoras theorem thing and we'll go for the right angle triangle. Suppose this will be the R, this will be the X, suppose this side can be the Y. So this is the magnitude. So for always triangle's law says that adjacent side, sum of the two adjacent sides, you can take anything, sum of the two adjacent sum of the two adjacent sides can be greater than or equal to the third side. It cannot be less than. Means if you add two sides, it cannot be less than the third side. So that's the one. So that is called the triangle inequality. Then the this inequality can be, if you take the mod of that one, or square root, like if you take r square is equal to x square plus y square. So that will give like this one. But it is in the complex, in the quantum state, we write this inner product will be only scalar. So this will give you the scalar. But don't forget, if you take this square root, then only it will be like that. That's why the square can be cancelled. X square plus y square is equal to r square. But here it is there. So this can be there. Similarly, this can also be, we can verify using some of the examples. So this holds good for the both the linear state as well as the quantum state. Linear vector space also and quantum state. So this example we solved yesterday. So you can take this example and first you try to find this very simple one. So here x is given, that is ket x is given and ket y is given in the basis of b1, b2, and here also mentioned that b1 and b2 are orthogonal basis. That means b1, b2 are like this. If it is orthogonal, what is this value? So first of all, these two are equal or not? Since in this particular problem we already got a1 over a2 is I by 2, then a2 over a1 can be minus I by 2. That we can see. But here, instead of that, this so in this case, this basis a1 and a2 are not orthogonal. We have such a thing. But here b1 and b2 are the basis, and these two bases are orthogonal bases they mentioned in that. So that means b1 b2, b1 over b2 or b2 over b2 can be equal, and that can be equal to orthogonal means can be 1. So in this case it is easy. Either you can take this value or this value, the answer cannot change. So it is simple. But in this case you can be careful. a1 over a2 is I by 2, then a2 over a1 can be minus I by 2. When you are substituting that, yesterday I heard see something like in between intermediate step, if I recollect, 13, just a second, I wrote somewhere. Yeah, so that is 4 plus 13 minus 6i square by 2 minus 6i square by 2. That means 17 plus 3 plus 3, totally it will give you 23. That is this value. But if you substitute, when you are taking this value multiplication, first if you are multiplying this with the cross term, this a1 a2, so you need to be a1 over a2 to write like this. And when you are writing this a2 a2, anyway it will be 1. But here when you are writing this a2 over a1, you need to write like that. Simply here you cannot interchange a1 a2 and a1 a2 here. So either you need to follow, one is a1 a2 and second is a2 a1. That means you can get this minus sign can be substituted. Otherwise the answer will be wrong. But in this case it is okay when it is orthogonal. So there is no imaginary term. Both the values are real and that is equal to 1. So that is simple. So but this first simple case, x plus y, ket x, ket y, both simply adding. So ket x is given here, ket y is given. Just they are asking the what is the addition of that one. Simply just add that their basic value. So b1 b1 you can add. But here this is the real value, this is imaginary. This is the real one, this is the imaginary. So now it is clear. You can see. Can anybody just quickly give that ket x plus ket y? What is x plus y? Or else we'll quickly proceed to the triangle inequality. Prove. Can you prove this triangle inequality? So for that you need to have this one will be the x, this will be the y. I just given this copied from the equation, but here the bases are b1 b2, but the values are x y. So instead of psi, the state can be represented as x. Phi, the state can be represented as y. So you need to take psi plus phi, that means x plus y. So you have already had here x plus y. Then this can be the x, norm of x, this can be the norm of y. So anybody done this? What is this value? Minus 1 plus 3i b1 plus minus 6i b2. So minus 5i b2. So this is minus 7i, this is plus 2i. When you add this b2 bases, both are imaginary, there is no real part. So 2i minus 7i, that is minus 5i, minus 5i b2. But here this is minus 1 plus 3i b2, b1. So that is a simple. If you take that mod of that one, means that one you can represent it as one, some a b c or something. If you want to express this in terms of matrix, you can also write like this. This b1 b2 are basis. So this is the b1 value. So 3i minus 1, that is minus 1 3i, and b2i b minus 5i. So this is the value. So but I'm trying to represent in a matrix form so that you can easily solve using your uh, even Excel sheet or the MATLAB code when you are having the multiple systems in it. So this one only B1, B2 and one simple one. So if you are having this one, you can also write simply using the same way. So then you can forget about this value. Then you can take the basis and this will be useful in the calculation. So when a set of equations are given in the quantum equations or the quantum state only, still you can able to write them in a matrix form like this, separating the basis with the quotient. Is it clear?
Yes, sir.
Okay. And we also discussed some of the gates which are useful, mainly Hadamard gate and Oracle operation and Pauli's gate. So the Pauli's gate will be just if you apply the Pauli's gate, then it will be like this. So this is the basic syntax of the Pauli's gate. Then Oracle, if you take, it will be create a loop -1 to the power of, then okay. So this is the Oracle operation. Then Hadamard operation, just one. This is also one, one -1. And anyway, there will be 1 over root 2 will be there. So that is the Hadamard operation or Hadamard gate. So simply you can replace this with, but you are expressing in an equation, you can write it as a H, matrix H. And phase shift, we didn't deal with that. Suppose if a vector or a quantum state, suppose this will be, and I forgot actually one of the advantage of the quantum thing is, suppose if we have 0 or 1 bit, so this can be represented, suppose, okay. Suppose either 1 or 0, so sign is there. Suppose this is only positive sign, so this we can express this as the state, and suppose we have the sign is assigned as the bit for classical. So we have only this one, but we don't have the real nature or intermediate state. But one or the quantum computing can also allow us the intermediate stage like this, either in between this stage. So that will be written like this. So that is the advantage of the quantum thing. And we also seen some of the advantages of the quantum computer. So computing speed is high. How it is fast? Because of it is having in a single stage of operation, in a single syntax, it can compute the parallel operation can be done. You can have the intermediate state. So these are the main operations involved in the uh, quantum computing. Is that okay? Should given one example here for using dice algorithm, how we can find the uh, sequence of operation like f of 0 or f of some function. It will be easy. Then we can factorization is anyway we can need to be follow our normal computing method, but text algorithm is somewhat simple. We can just find this one using uh, with sequence of code. So we can practice. We should have practiced one example. Given space is like only 4 or 5 bits. Suppose like the domain is defined. So in this we need to find, suppose our target value is 1. When we are looking for that, how we can, how many sequences are needed and how many iterations are needed to perform our value, both in a Grover's method or means quantum method and the classical method. Then you might have seen this thing. But it is difficult to take practical session or the hands-on session with this. I thought I didn't ask the organizers for their testing. So I'm really sorry for that. Otherwise, hope it is very clear how the operations are there. I'm stopping here. Please let me know if you need anything is not clear or any kind of doubt you have. Is all the participants are from the computer science department or like any mechanical or civil, electrical?
Electrical departments also is there, sir. Computer department, electrical department,
Okay. For computers,
electrical communication department.
okay. Even ECG and computers no need to teach this some of the algorithms, means basic computing things. They might know very well. But for computer, for mechanical or civil, it will be somewhat new to them.
Yes, sir. More participation asking give to presentation presenting PPT.
Yeah, that you add, no, you can send it, or if I just add something, if the time permits, uh,
Okay, sir.
that unconditional gates are there, that slide is missing, then it is absolutely fine. We can send it to them.
It is new topic for us. Please send PPT. There are more participation asking, sir.
Yeah, and even if it is the PPT is not enough to you, you can also take the reference and try to read whenever time permits. And one more other easy way is that you can also take some of the NPTEL courses for quantum computing. I think IIT Bombay is there. So you can just check there, it will be easy. You can see physically the presentation and the explanation. Otherwise, if it is you are only reading in the reference books and all, somewhat difficult. Okay, I'll include some of the gates or something in the reference links also there. So in the reference, I will give algorithm references and the quantum gate separate link for the quantum gates. Then it will be useful.
Okay, sir. Thank you, sir, for clear explanation of more algorithms,
Okay.
different types of algorithms.
Yeah.
Just
Thank
like
you. Feel free to ask, even you can send email or anything for any discussion or anything. Thank you very much. Thank you, Bhavya, for supporting.
sir. Thank you so much, sir.
Yeah, thank you all.
Thank you, sir. Sir is explaining more quantum computing algorithms, just like detached algorithm, Grover's algorithm, source factorization. These algorithms is are explaining. Next section is start sharp 2 o'clock. Then join the same link. Thank you. Thank you so much. Please join the same link. Before 5 minutes, you will join. Thank you. If any queries, post in chat box. Each and every PPT and YouTube links and recorded videos, entire thing is posting in WhatsApp link. Please check that one. Afternoon section it will start 2 p.m. That is most interesting topic, quantum computing and using phonetics. Then please join before 5 minutes. Thank you. Thank you participation. Thank you, sir.